This is the first lesson on permutations and combinations. And I'm going to begin with the fundamental counting principle, which is really the foundation for almost everything that you do in this unit. So mastery of this particular concept is critical. So to begin, let's start with this scenario. We've got 4 roads going from Seebe, Alberta to Westward Ho, Alberta. 3 roads from Westward Ho to Consort, Alberta. And then once you're in Consort, you've got a choice of 2 roads to get to Goodsoil, Saskatchewan. Okay. How many different routes can be taken to travel from Seebe to Goodsoil? Now, this question does require a bit of a definition. A route would mean that you take, say, one road from Seebe to Westward Ho, then you take another highway to Consort, and then you take another highway to Goodsoil. That makes up a route. If you change one of those highways, so if you take, say, Highway 12 instead of Highway 11A to get from Westward Ho to Consort, then you have changed the route. So all it takes is one segment to change in the travel agenda, and then you've got a different route. Now this question can be as complicated as you want. I mean, you could think about it through, okay, I'm taking Highway 1A, then I'm going to take Highway 22, then I'm going to take Highway 12, etc. like that, and then count them all. But it's much easier if you draw a little diagram starting at Seebe and indicate that from Seebe to Westward Ho there are a choice of 4 roads that you could take. And then the next section of the journey to Consort, there are 3 roads that you could take. Choice of 3. You can only take one of them. And then to get from Consort to Goodsoil, there's a choice of 2 roads. So 4, 3, and 2, and then you're in Goodsoil. And these each represent the number of choices that you could make. And then we multiply them together. 4 times 3 times 2 is equal to 24 routes from Seebe to Goodsoil, Saskatchewan. Now, the question could go on. How many routes from Seebe to Goodsoil and back if no road may be taken more than once? So this means that you're doing the same thing that we just did to get to Goodsoil, but now on the way back, we cannot take the same road that we took on the way there. And a lot of people get this question wrong. They do things like they take the previous answer, double it, sometimes subtract 1, do all sorts of weird things. But the key to doing these type of arrangements properly is to get a little diagram drawn and ask yourself that key question: how many choices? So we do know this. Seebe to Westward Ho to Consort to Goodsoil, we have all these. That's 24 choices. But you're in Goodsoil, Saskatchewan right now, and you're headed back to Consort. And instead of having a choice of 2 roads, you now just have a choice of 1 road. And now that you're in Consort and you're looking to get to Westward Ho, there were 3 roads you could have taken, but you can't take the one you took on the way there, so now you just have 2. And then from Westward Ho to Seebe, instead of having those 4 choices, you now just have 3 choices. So if you put the whole thing together, you're going to have 4 times 3 times 2 times 1 times 2 times 3. So there's 144 routes from Seebe to Goodsoil and back without taking a road more than once. So that's what we're going to be up against in this unit, and changing the way we think so that we break down every question like this that is asking how many choices, how many ways, we break it down into each segment of the journey, or whichever we have like that, if it's a journey. Something you're probably wondering too is, what's with this multiplication? Why are we always multiplying? And that is based on the fundamental counting principle. And the fundamental counting principle goes like this. If the first choice can be made in m ways, and the second in n ways, then there are m times n ways to select m and n. Okay? What it really means is this word and if you've taken some of the Math 20 topics, you might recall this. The word and means multiply. It always implies multiplication. So if you are looking to choose to get from Seebe to Goodsoil, you take the number of roads for each part of it and you multiply. You don't add. Another way of looking at it is a really common question is outfits that people wear. If you have 4 shirts and 3 pairs of pants and you wanted to work out the number of outfits you could wear, different outfits, you could go 4 times 3 is 12 different outfits. It wouldn't be 4 plus 3 is 7. So the question is pants and a shirt, not pants or a shirt. And as you'll see later on, the word or implies addition. So this is a typical question too. Bicycle license plates in some areas are issued using 2 letters and 1 digit, ordered letter, digit, letter. How many different plates could be issued? So we do the same thing. Now I'm going to call these slot diagrams, and I always draw these when I'm working through these. In one form or the other, you need to. And you ask yourself, well, in the first position on the license plate, it has to be a letter. The second position has to be a digit, and then the third would be a letter. So we're set up like this: letter, digit, letter. And the number of choices for letters, well, we have 26 letters that we could select from. There's nothing here that says that the alphabet has been altered in any way. And then for digits, we actually have 10 choices there, including 0, which again doesn't seem to be any reason we cannot include 0, and then 26 letters for the last one. And according to the fundamental counting principle, we do in fact multiply. And if you do that, you will get 6760 different plates can be issued. So that's a fairly typical question. Let's do another one. So really the rest of this lesson is just going to include about 8 or 9 more examples. At any point, if you want to do them yourself, just pause me, do it, and then check the work afterwards to see if you got it. That's really good practice. These questions do require practice. Most people, when they're doing them, will get a lot of them wrong at the start. They check the answers in the back, and then they see that something went wrong, and then they try it again. In most math questions, that's not considered all that good because you're not doing too well. The answer is there just to confirm that you knew what you're doing. You may not feel you know what you're doing with a question and still get it right for these ones. Or you may feel you do know what you're doing and get it wrong. So it's really hard to have confidence in them until you've done enough, checked your answers, and then you can say, okay, I know how to handle this type of question. But the learning is a little bit different than it is for most math topics. How many 4-digit numbers are there? You really have to go slow and take extreme care at each step. So for the 4-digit numbers, we take a look at the slots again. Now this question has a trick to it, sort of. With a digit, with a number, like for example, if you had 2, 5, 6, 2, this is a 4-digit number. Few would argue. However, 0, 5, 3, 9, this is not a 4-digit number. If it's a code, well, that's different, like a password or something. But because of the 0 in front, you can't have that with digits. So this cannot have 0 in the front. So that changes things because you're always asking yourself how many choices. Now there's 10 digits in there. So instead of having 10, for the first position we have 9. And remember, the question again is how many choices for for any of these positions. So 9 choices for the first one. We then have 10 choices for the second, because it's freestyle. You can have anything there. And then you have 10 again for the next one, 10 again for the next one. And then all you have to do is multiply straight through. So that's equal to 9,000 numbers. So most of the questions have some form of restriction like that on them. Let's try another one. How many 4-digit even numbers are there? I'm going to do this 2 ways. One is the same way that we did before. Ask ourselves how many choices. But also keep in mind this issue of evenness. If you had this number, say 7, 9, 3, 4, and then you compare that to 2, 8, 6, 1. The first number is even. The last number is not. So evenness depends on the last digit. The last digit is even. We don't care about the others. So it must end in 0, 2, 4, 6, or 8 in order for it to be an even number. Go to the restriction first. So when I see this question, I go right to the very end, and I note that there are 5 choices for that last one. That takes care of the evenness. And then go to the front and work your way down. As always, we have to consider the fact that it cannot be 0 at the front, so we only have 9 choices. But because there's nothing in it to suggest that repeats are not okay, we can just put in 9 and then 10 and then 10 and then 5. So that's equal to 4,500. Now that's the conventional way. The other way is just to think. There's 9,000 total 4-digit numbers. You know that from the previous question. Divided by 2. Half of them are even, half of them are odd. So that's an acceptable way to do it. Next question. How many ways can the 15-member .001 Losers Club select a president, a vice president, and a secretary if no one can hold more than one position? So that means that if you're the president, you cannot be the vice president or the secretary. So we set it up. It doesn't really matter which order you do it, but I'll go president, VP, and secretary and ask myself that question again. How many choices? Now there's 15 people in this club, and it doesn't say anything about there being any other restrictions, so it's safe to say that you've got 15 choices for the first position. 15 people who could be president. And then for the vice president, well, there's only 14 that are in the running now because one of them has been assigned the role of president. And then 13 for the secretary. And then you just multiply it through. 15 times 14 times 13. And in doing that, we will get 2,730 possible executives. Next question, how many different 9-player batting orders can Coach Shultz form from a 10-person team if Boris must bat cleanup, which is fourth, if you don't know your baseball? There is one assumption, and that is that there is only one guy named Boris on your team. We do the same thing though. We draw the slots. This is the first batter, or lead off. Here's your second, third, fourth. You don't need to label all these once you know what you're doing, but you do have to make sure that you've got 9 of them. Go to the restriction, which is the fourth batter. And that has to be Boris. There is only one guy named Boris on the team, so you have one choice for that position. And at that stage, we can go to the front. It is freestyle. There's 10 people on the team. One of them has been assigned to bat fourth. So now we have 9 people left. So we have 9 people that could go in the first position. We then have 8 choices for the second, 7 for the third, fourth is taken care of, so 6 for the fifth, 5, 4, 3, and 2 choices for the ninth. And that makes sense because one person is going to have to stay. So just multiply 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2. And you'll get a big number. So 362,880 batting orders. So that's the idea. Let's try a few more. A quiz has 10 true-false questions. How many different ways can a student answer these questions if they answer all the questions? So you're sitting there writing this short little quiz, and your choices are true or false. For some reason, people make mistakes in this one, just in the setup. They get mixed up in what's going on. But really, you've got these 10 questions in front of you, and at each question, you have a choice. So this is question number 1. And then you don't need to write all this in, etc. But I will. I'll put at least etc. for it. You're sitting there in front of question number 1. You've got 2 choices, true or false. You get to question number 2, the same 2 choices. In fact, that's never going to change. You have 2 choices for each of the questions. So it's really just 2 multiplied by itself 10 times, or 2 to the exponent of 10, which is equal to 1,024 ways. So if this had been rewritten as a probability question, it would have been something like, what is the probability that you, by guessing, get 100%? And that would mean that you'd have, to get them all right, would mean that you'd be, your probability would be 1 out of 1,024. So not very good. Let's try the same sort of question, but with a twist. The same quiz, but this time the student doesn't necessarily have to answer all the questions. And that makes a difference because in the previous one, we assumed that the person was answering for everything, but not every student answers all the time. So in this case, for question number 1, you could answer true, you could answer false, or you could no answer. So you have 3 choices. So true, false, or no answer. And that would be true all the way down. So you could, in theory, submit the quiz without doing any of the work at all. Just leave each one of them blank. Or you could leave some of them blank. And that would then increase the number of possibilities to 59,049 ways. So there is thinking involved in these questions, but it usually comes down to that question, how many choices? How many three-letter words, arrangements consisting of a vowel between two consonants can be made using the letters of the word certain if no letter may be repeated? Now this issue is going to come up again. I refer to it as a word, but in fact it is just an arrangement of letters. The word implies that it makes sense, and these do not have to. They're just an arrangement of letters. So from here on in, I'll probably just call them words, and what I really mean is an arrangement. This one has a restriction because it has to be from the word certain. And if we were to put in more information, the vowel has to be between two consonants. So vowel there, and then consonant, consonant. Has to be that way. And in this word certain, we have 1, 2, 3, 4 consonants. So we have a choice of 4 consonants for that one. I'm going to go right to the end and finish off the consonants. Because you're multiplying, it really doesn't matter which order you do these ones. You can jump around because it doesn't affect the order of operations. We have 3 consonants left because no letter may be repeated. So when we put C in the first position, then we cannot put C in the last position. And then for vowels, we have 1, 2, 3 vowels. So now we multiply according to the fundamental counting principle, and we get 36 different words. Next question, how many 3-digit numbers less than 500 can be formed using the digits 1, 2, 4, 6, 8, 9? So this is not really introducing any new concepts, but it does force us to look at some restrictions and a pool of numbers that we can select from. It's a 3-digit number, but less than 500. Now, being less than 500 means that it must start with, well, 1, 2, or 4. Because that's going to ensure that it's less than 500. So you've got 3 choices for the second one. And there's nothing in here that says you cannot repeat. So there would have to be something otherwise to tell you that. Because normally with your numbers, it's okay to have like 5, 5, 2, or repeat numbers. So there would have to be something in the question saying that repeats are not permissible. So 3 choices for the first, and then following that we have, it's freestyle, it's open-ended. We have 6 and we have 6. And then you can just multiply it right out. And that will give you 108 numbers. Next question. These 2 questions I'm going to look at are, for lack of a better word, special cases. They would be considered difficult questions. They don't introduce any new concepts, but normally if you're given questions like these next ones, you will struggle with them unless you've seen the method. So the first one of these type is how many even 3-digit numbers have no repeated digits? Now we've already done even digits, or even numbers, so we know the method for that. But in this case, it's having no repeated digits. So that complicates things. So I'm going to look at this 2 ways. Now the one method that is sort of the traditional method is to think like this. We have 2 restrictions. If they're even, and then they're not having any repeated. Now if they're even, it must end, as we know, in 0, 2, 4, 6, or 8. And the problem with this question is that we really have 2 different scenarios, all because of that 0, because we cannot start with 0. So we break it down like this. The first scenario is the number of possibilities if it begins with 0. Or excuse me, ends with 0. Makes a little more sense. So if we put the 0 in the back position, and that makes it even, then that has an effect on the first position because we can't repeat. So if we put the 0 there, it means that it could not be a 0 at the front. Now it couldn't be a 0 at the start anyways. So we can put anything except 0 there. So we would have all these other digits to select from, which would be, in fact, 9. 1, 2, all the way up to 9. And then in the second position, we can put anything there except the 0, which is already spoken for, and whatever we put in the front. So we have 8. And then the second scenario is that it doesn't end in 0. So that would mean if it's going to be even, it would have to be either 2, 4, 6, or 8. So we have 4 choices for the last position. And then when we go to the front, so notice how I did that restriction first. I go to the front, and it's true that 0 is possible because we didn't put it in the last position. But unfortunately, we cannot put 0 there because it's to be a digit number, 3-digit number, it can't start with 0. So we only have 8 choices. So this would be, it cannot begin with 0. When we get to the second position, however, we would be down by 1, but now that we can use 0, we have 8 choices. So we would have everything except the 2 other numbers that we put in those first and third positions. And here's the other, I said that there was no real new concepts, but there kind of is. The word between them is or. It can either be one position or it can be the other. And we will focus on this more soon, but or translates into plus. So this is a case where we do add these two cases together. So 9 times 8 times 1 is 72. And then 8 times 8 times 4 is 256. And that gives us 328. This is considered a difficult question. Real thinker. I'm going to do this question again, although I'm going to use a different method for it. See if this makes more sense to you. So the other method that you could use is to think like this. Forget about the odd and the even for a second. I'm going to take a look for the first one as the total number of 3-digit numbers. So forget about odd and even. And for the number of 3-digit numbers, because we cannot start with 0, we have 9 choices. And then for the second position, well, now we can use 0. We just can't use that first number, so there's 9 choices there. And then 8 going down by 1. And then I'm going to, for the second group of slots, I'm going to consider the number of odd. The number of odd digits simply means that it ends in 1, 3, 5, 7, or 9. So that means that we have a choice, a total of 5 choices for the last position. And then in the front position, we cannot use one of the digits we selected for the last, nor can we have 0. So there's 8 choices for the first position. And then for the second position, we can't have 0, nor can we have the numbers that we have previously used. So that would give us 8 choices there. And in this case, if I want the number of even numbers, I just subtract. I take the total minus the ones we don't want. And that will give us the number we do want. So 9 times 9 times 8 is 648. And then we subtract 320. And we do end up with the same number, 328 numbers. So this is using the sort of method of indirect solving, where you subtract away the ones you do not want. And that leaves you with the ones you do. But either way, this is a tricky question. Let's do one more and then call it a day. How many different sums of money can be formed from 5 pennies, 2 nickels, 3 dimes, and 1 quarter? The best method to do this is first off to do a little bit of thinking about the question and then set up these 5 slots. So this means that you've got, you could think of a jar with 5 pennies, 2 nickels, 3 dimes, and 1 quarter. And how many different individual sort of configurations could you make? Now, some of the questions like this that you're going to get will tell you, well, it's got to be 2 coins. It's got to be 3 coins. And that helps in a way. But this doesn't, because it could be 1 coin. It could be 2 coins. It could be 3 coins. And then, of course, it could be 3 pennies. It could be, 2 nickels and a dime, so on like that. So there's very many possibilities like that. So what we do with this question then to make it work is we take a look at each of the type of coins. Pennies, nickels, dimes, pennies, nickels, dimes, and quarters. What am I doing with that last one there? Okay, let's get rid of that. And then we ask ourselves, if we're going to select a certain number of coins, with respect to the pennies, what is the number of choices that we could have? We could either have 5 pennies, we could have 4 pennies, 3 pennies, 2 pennies, 1 penny, or even 0 pennies. So there's actually 6 choices. And the same thing with the nickels. Your collection of coins that you select, you could have 2. You could select 2 nickels, you could select 1 nickel, or 0 nickels. So you got 3 choices. And then dimes would be the same. You could have 3, you could have 2, you could have 1, or 0. So that's 4. And then finally with the quarter, there would be 2 choices. And then we multiply them together. 6 times 3 times 4 times 2 is 144. But now you must think. Something might have been troubling you. If you're going to have a sum of money, you have to have something. And the one thing that we cannot have is no coins at all. So there's one possibility that we subtract away, and that's where you've selected 0 pennies, 0 nickels, 0 dimes, and 0 quarters. So to get your answer, then, you would subtract 1, and that will give you 143 different sums. Not the sort of thing that would occur to you normally. So that's it for this lesson. The next lesson will give you some sort of calculator operations and some definitions and some additional methods to solve problems. But in fact, if you apply what you've learned here, well, you can pass the exam already. Thank you for your time.